Right, so welcome to our another segment of computer organization and architecture. We are discussing computer memory system. Last time we covered a number of aspects of the topic, and today we just want to uh, briefly discuss the concept of memory interleaving. So this is one of the techniques that is used to, um, streamline the way memory is accessed to grant more performance to the processor, in light of the fact that, we've said that oftentimes we have memory is the one that bottlenecks the processor memory interface and slowing down the performance of the entire computer system. So we want to start with a simple analogy that we are all probably all used to, or we can understand, and to help us understand how memory interleaving really works. So imagine the concept of a market, that we're all used to, um, and you can have, two main variations to the market. One is where you have, a traditional market, a single market, uh, where, all items are sold. It could be your vegetables, it could be your fruits, it could be your small items like your flour and your oils, your soaps, your bread, your juices, and all are sold in this traditional single market. So in that setup, um, obviously you have one point of sale. Of course, we are not referring to the device per se, but all customers come to the market and they get the items that they want to get. They go to one point to be serviced in terms of paying and exiting the market. And if there are many people, maybe it's a festive season or it's a high peak period, then to, to make sure that the market continues working, and the customers that are there are serviced, then there might be a need for a line, and for customers to wait for service by queuing, right? Because you only have a single market, there's only one point of sale, and you can't, support multiple servicing of customers at the same time. And so this is the first setup, all right, where your resources that customers want inside the market can only be accessed one customer at a time, and there's no multiple access in terms of checkout. Of course, this has its own problems, obviously, in terms of the queuing effect, which will slow down performance of your market, which is really what happens then in memory system that does not have interleaving. You have one big block of memory which is not partitioned or interleaved, and all requests go to this one module. Okay. All words that the processor wants to access stored within this one module. And because there's one module with one single point of service, you can support multiple customer requests at the same time. So every request for a word in memory is serviced by this one module. Of course, like we just said, this creates a problem of performance bottleneck, where some requests will have to be queued while others are being serviced. So one way that this can be streamlined, or what we see in our markets in a day-to-day, is the concept of stalls. Just as we see in this diagram, the concept of stalls, and the stalls can actually assume two classes, where in the first class, you have a stall that is specialized for every item. Of course, the concept of a stall means each stall has a person in charge of it, who owns it. So you can have a stall for tomatoes, next stall is for apples, the next stall is for pumpkins, the next stall is for apples, and you see that. So unlike in a traditional setting where every customer now has to go through one checkout point, each stall is actually a checkout point by itself, but the stalls combined, they create a market. So if you have a customer looking for tomatoes, they go straight to the tomato stores, and they get their tomatoes, at the same time as the customer is getting tomatoes from the tomato stall. You can have someone who needs avocados being serviced by the avo store. So that's the idea. Then the concept of stores also, can be in the form of specialized stores, not like the basic ones that we just discussed, where each store sells one item. Or you can have, like, a specialized store, for example, for vegetables. So all vegetables are sold at that store. And then you have another specialized stores for fruits. All fruits are sold at that store, meaning uh, per, per stall, you can get multiple items. You don't need to uh, move between stalls too much, especially if you're just coming to the market to buy fruits. Then you can simply send all your requests to that single stall, for bananas, for apples, and for peaches, for oranges, get all of them from the same store. So, of course, the two configurations have, their pros and cons, and how they affect the uh, performance of your market. But it's it's better than the traditional um, non-store based market. Of course, that comes with the cost as well, because you now have to partition your market, and each stall now needs someone to manage it, to process checkouts, which raises the amount of resources required, uh, to create and run a, a, a stall-based market. So the stalls now brings or mirror the concept of interleaving, where you partition your memory into modules, okay? And each module really is, it's a small memory that can be accessed independently, and can service processor requests. Okay, not sure what just happened here. Um, Let me see. All right. Yes. So that's the idea, with your um, simple store-based, being your one kind of memory interleaving, and the other one being another kind of memory interleaving. So with that in place, you can simply understand what we are introducing, the concept of memory interleaving, which say a technique we use to improve the speed of access to memory in computers. How? By partitioning memory into modules so that the addresses, are distributed not to one module, but to multiple modules, which can be accessed simultaneously. And by us having simultaneous access, it means we have a high speed of access, and we can access multiple words, we can read and write multiple words at the same time, so that gives us a bigger bandwidth in terms of access to memory. And of course, the main goal is to increase data throughput, which is the amount of data or the amount of bytes that we can send or retrieve from memory at the same time, and therefore reduce the memory access bottlenecks. So we want memory to be fast so that it quickly responds to processor requests, and then that makes our computer even faster as a whole. So we have two types. Of course, there are others, but these are the main types that we want to consider. Low order, where the consecutive memory addresses are distributed across multiple modules, meaning this is the tomato stall, banana stall, apple stall, the simple one, where if you want multiple fruits, okay, you came to the market to buy multiple fruits, you still have to visit multiple consecutive stores to get those fruits. You go to the first one, you get apples. You go to the second one, you get bananas. You go to the third one, you get peaches. You see that? So consecutive addresses. So if you have an array, for example, sitting, yes, like your array of size, 10 bytes or 10 words per se, actually. Then the first word will be sitting on the first module. The second one is sitting on the second module. The third one on the third module, and depending on the number of modules you have, then the addresses will be interleaved across those modules. Then the higher order is the specialized store kind of setup, where blocks of memory, it could be 0 to 10, and they are allocated to a module. 11 to 20 allocated to a module. 21 to 30 allocated to module. So if the kind of memory accesses that your processor is trying to make a block, so the processor is accessing address 0, address 1, address 2, address 1, 0, then those addresses can be localized to that one module that is housing them. So, of course, the two interleaving methods can support, various configurations depending on the kind of application profile that your computer system is supporting, right? So in a case of an application with quite random accesses, then you can do well with a low order because your processor is accessing random addresses. So it's good to distribute those addresses across multiple modules so that you get the high bandwidth that we are referring to. But if the processor is often accessing words that are close to each other, in blocks, then you can get better performance from high order because while distributing addresses across multiple modules gives you better bandwidth, but remember the extra work that goes into actually running those modules as well, powering them as well, can actually slow down performance, especially for addresses that are close to each other. So, because already we have discussed the concept of banks and main memory, how you make bigger, larger memory by composing multiple banks. And just as we have 8 banks here of 16 megabytes each, together they create your 128 megabytes. And then we have 8 this side and 8 this side. Together they create your what? They create your 2 gigs RAM memory. So in terms of high order, high because suppose this is like your memory address bits, which has 26 bits, for example, from 0 to 25. Okay. So up here we have the address bit, and then we also we have how they are used, right? So it's called higher order because in high order interleaving, you have a module, the module, the module, the module, the module, the module, the module, module. So the higher bit, right, of your memory address. So, for example, in this case, because we have 8 modules, and therefore for 8 modules we need 3 bits, to be able to select each of the modules. So those 3 bits are, located at the higher end of your memory address, being from 25 to 22. So those 3 bits, the high end of your address, are used to select the bank or they're used to select the module. Okay. For example, if they are 0, then the module, like if it's 000, okay, then the module that we are accessing is module 0, okay. If it's 001, then the module that we are accessing is module 1, right? And then you can see that this gives you that block access because address 0, address 1, address 2, address 3, right? All of them are housed within module 0, right? And so it's like a block of addresses housed within one module. Okay, it's like your fruits, your vegetables, your breads, your drinks, all housed within one store. Okay, so that if your processor has that block profile of accesses to memory, they are all accessing one bank, one module, right? Of course, this is the most simplest and the most common way. The challenge with it is the is the idling problem, okay? Especially if the application profile that your computer is running does not have this block um, uh, profile of accesses. So, I mean, you have random memory accesses. You have 0, you have 20, you have 13, you have 9, and, so what's going to happen is that you will access 0 here, okay? Um, and then you have to access 20 at module 5, you have to access 9 at module 2, right? But if the accesses are, in a block profile where, I mean, it's like 20, 22, 21, 16, 17, okay, then you have the problem of idling for the other modules, where the only 2 modules, 4 and 5, are in usage, okay? So therefore, the performance of one module now becomes a bottleneck, determining the performance of your memory, because all accesses are hitting that module. Therefore, its performance will give us the performance of the entire memory system. So here's an example. Let's say the task is to design 64 kilobytes of memory using 16 kilobytes, um, small blocks, right? So you have the goal of building 64 kilobytes, and the smaller chips you have are 16 kilobytes. So firstly, you determine how many of these small modules you need. You simply divide 16 kilobytes with, into 64 kilobytes, which gives you 4. Of course, you need to understand, this notation as well. This is like 16 kilo times 8 bits. Okay. So, hence why we call it 16 kilobyte. The 8 bits, each of them give you a byte. So these devices have 16 kilo, slots, 1 byte each, uh, for storage. So we divide the 2, it gives us 4, and therefore we need 4 of them. Now, the next, task is to determine the number of address lines that are required, um, to address the larger memory, and also the number of address lines which are required to address the smaller memory. And then now, since it's high order, okay, pick those higher bits from the address line and use them to select the bank, just as we just illustrated here, that you have an address of 26, um, 26 bits. And so because we have 8 modules, so for the 8 modules, we will be able to interleave them together. We need 3 bits, which will be used to select each of the modules. So those 3 bits, we pull them from the a high order end of our address, which is 25 to 22. So, but the bigger address, which is this one, okay, which is 26 inside. That's the address of your larger memory, okay, which you are building from the smaller ones, okay. But the larger address, part of it gives you bank select, and then the smaller ones, okay, the smaller addresses, which is 2120. These are the ones, therefore, which are used to address the smaller modules. Okay, address the smaller modules. So, for example, before we go to the exercise that we are doing, let's say you have an address, like 0, okay, and then what you have? You have 0, 0, 0. Okay, there are 26. Let's just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 6. So this is your address, okay? And then we are saying the top 3 bits, okay? They are used to select the bank. So let's say this is 1 here, and then the rest of the bits, okay, are used to select the address inside the module. So what you do, you can select this, right? Maybe let's give them a, okay, it's not allowing, it's fine. You can select this, the first 3, okay, 0, 1, 0, the value thereof is actually 2, which means the bank to access, like the bank that supports, or the bank that serves this address is actually module 2 or bank 2. And then the rest of the other 22 bits, okay, this one, which is 1, um, you know, okay, we didn't do it well because 1 now falls on module what? Module um, 0. But then that one will give you the address within the module 2, okay, that you need to access or to address to find the word that you're looking for. So what we need to do is just fix this. Let's just fix this. Okay. So we'll need something of this sort. Okay. Already 1, 0, 1. Okay. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this would be something like this. Okay. Where you have 0, 1, 0, it gives you module 2. Okay. The rest of the bits, 0, 0, 0, 1, 0, 0, they give you what? They give you the address now, which is 8. Okay. Within your module, that you want to access. So what we are doing here, okay, the idea here really is, since we want to access 16 kilobytes, no, like we want to access 64 kilobytes of memory, okay? We want to access 64 kilo, the number of bytes we want to access are 64 kilo, and where each of those slots are byte sized. So we rewrite 64 kilo in base 2, okay, as close as possible to 64 as we can. So we have 65, 36 being the closest, which is 2 to the power 16, meaning to address 64 kilobytes, okay, we need 16 address lines. The same way that we just said here, let's come here. Like, of course, okay, here we did not really discuss addressing issues per se, but let's say you had, um, let's say we had um, 8 bytes, okay, of memory to address. And the question is, how many address lines do we need to address this? If we call it log, um, you know, base 2, okay, of what? Of 8. Log base 2 of 8, which is what? Which is 3. Each of the 3 bits will be used to uniquely address each of the 8 bytes, okay? And if it is 16, you know, 16 bytes is the same thing. Log base 2 of what? Of 16 is going to give us what? 4, all right? So up there, what we did is log base 2 of what? Of 64, okay? 64 kilo, okay? Or 64 kilo or 64,000, okay? Of course, it's going to give you 15 point something, okay? But you can't use 15 point something address lines, So we round that to 60, which actually gives us 65.536. And we do the same thing for the address lines required to address the smaller, modules, which is going to be log base 16 of log base 2 of 16K. It gives us what? 14 address lines that we need. So the lower 14 address lines will go straight to each of the chips. Okay, so you have your A0 to A15. This is like the parent address which goes to your memory. Okay, where if this is your memory, okay, this is your memory. The processor sees it as one module, but in structure, it's built by, interleaving multiple modules. So because it is 64 kilobytes, then we need 16 address lines, which is A0 to A15, to address it. But in terms of how those 16 address lines are used, now is that is detailed by the kind of interleaving that we are using. So for this case, because we are using high order, the high end of the 16, okay, meaning 14 to 15, okay, why 14 to 15? We said we need 4 devices, okay, because there are 4, which means we need 2 bits, which we can use to decode the module that we need to access. So 00 will go to module 1, 01 will go to module 2, 10 will go to yes, to module what? Yes, 00 is 001 is 1, 10 is 2, and then 11 is 3. Okay. Then the rest of the bits, okay, the rest of the bits, lower bits, A0 to A13, now they become the actual memory address bits, which are used to fire up each of the smaller modules. Of course, we said they need 14 address lines. Okay, so you will have A0 to A13 for module 0, A0 to 13 for module 1, module 2, and for module 3. Okay, where each of them they have 16 kilobytes, 16 kilobytes, 16 kilobytes. And then, of course, you have those control lines for either reading or writing. And then you have the control lines which are used, to select that chip, depending on the address that we have at the terminals. And if it is an address that has the higher order bit being 0, then the decoder will, end that 0 into 00, okay, which will select the first bank. If it's an address that has maybe 10, the decoder will, like it, the decoder will end that 2 into 10, which will fire up the um, third module. Okay, this is what we are showing here. Essentially, 14 address bits connect to all devices in common, and then the blue address bits used to generate chip select input. So that's the idea. That's how high order memory interleaving works, and equally the same thing applies for low order. Only that now we use the lower bit, okay, to select the module, okay. Uh, Hence why uh, consecutive addresses, will be distributed across multiple modules. Why? Because the lower bits are the ones that are used to select the module. So if you have 000, that's one module. Once you step to 001, that's another module. 010, that's another module. Okay. Yes. 101, that's another module. So um, that's the idea. So this is the end, guys. We will do more examples to help reinforce this concept.